Hi everyone, welcome to Recitation 0.24 on saving and loading models. I'm Nishok and today we'll be covering how to properly save your train models and load them back for inference or continued training. Now, first let me walk you through what we'll cover in today's session. We have six main topics that will give you a complete understanding of model checkpointing. First, we'll start with the fundamental question. What exactly is model checkpointing? Second, we'll examine the complete flow of checkpointing, how data moves from your training session to storage and back again. This gives you the bigger picture of the entire process. Third, we'll get hands-on with torch.save, the primary function you'll be using for saving models locally. Fourth, we'll explore what actually inside those saved files, the weights and biases that make up your trained model. Fifth, we'll cover the loading process, how to bring your saved models back to life and restore all the parameters correctly. Finally, we'll work through a complete dummy model example that ties everything together so that you can see the entire workflow in action. So, moving on to the first question, what is checkpointing? Checkpointing is essentially creating a snapshot of your entire training state at a specific point in time. When we checkpoint, we are saving three critical pieces of information. First is the model weights. These are the learned parameters that represent all the knowledge your model has acquired. Second is the optimizer and the scheduler shapes. This includes momentum terms, learning the rate schedules, and other optimizer specific information. And third, current epoch and metrics. So you know exactly where you were in training and how well your model was performing. Now, why is this so important? Why are we checkpointing? So there are three key reasons. First is crash recovery. Whenever there's a hardware fail or power goes out, the process gets killed. With checkpoints, you can resume training from your last saved state instead of losing days of work. Second, you can roll back to the best performance. Sometimes your model starts to overfitting up to epoch 55 or 60, but was performing perfectly at epoch 30. With checkpoints, you can easily roll back to that optimal point. And the final reason is branching experiments. You can save a checkpoint and then try different optimizers, learning rates, or architectures from that exact same starting point. This makes control experimentation much more manageable. Now let's look at the complete flow of how checkpointing works. This diagram basically shows the main steps in the checkpoint lifecycle. So everything starts here, the local session. This is where you are actively training or running inference with your model. Your model exists in GPU or CPU memory and you are iterating through your training loop. So the first step is save using torch.save. This takes your model's current state from memory and serializes it into a file. PyTorch typically saves these as like a .pth files which contain all the information we discussed earlier. The checkpoint gets written to local storage, your hard drive or SSD, and these .pth files contain everything needed to recreate your model's exact state. So the step two is upload. This is optional but highly recommended. You can upload your checkpoints to external service like 1B, which we use in our course, like which is weights and biases, and this provides cloud storage, versioning, and easy sharing capabilities. Step 3 is download. When you need to retrieve a checkpoint either from your local storage or from a crowd storage like 1B, you just download the PTH file. And the fourth step is load. Using torch.load and model.load state dict, this takes the serialized checkpoint file and reconstructs your model state in memory, bringing it back to exactly where it was when you saved it. Like you can notice one thing, this is like a cycle. You can save, upload, download, and load as many times as needed throughout your project lifecycle. This flexibility is what makes checkpointing so powerful for iterative deep learning projects or your assignments in the coursework. Now, let's look at how to create a checkpoint. So, now first let's look at the practical implementation of saving models locally. As I mentioned earlier, torch.save uses Python's pickling to serialize the data into a binary format. First, we define the path with descriptive naming, as you can see in the first line. Then we save a comprehensive dictionary containing multiple components like model.stateDict. This captures all the learned parameters, and optimizer.stateDict and scheduler.stateDict. Like this basically preserves training state for proper resumption, and the metadata like current epoch and loss tracking progress are also there. All this information gets saved as a .pth file to a local storage. Now we can talk about a warnb integration. This like saving to a warnb cloud storage. So first you must call warnb.init, which is like initialization uh, step before your trading loop starts. So this is where you initialize it. Then option one is using artifacts. You can create it with artifact, and basically you add your checkpoint and you upload to cloud, like using this run log artifact. But option two is simpler. You can directly use 1b.save directly to upload the file. The artifact approach provides better organization and versioning of production workflows. Now Moonchen is going to walk you through loading a checkpoint and give a trial example of how that notebook works.
Okay, let's talk about how to load a saved checkpoint. This is especially useful if your training was interrupted. For example, if your collab session crashed. In that case, even though you lost everything in memory, as long as you save your model checkpoint, you can reload it and resume training exactly where you left off. No need to start from scratch. Now, let's see how to do that. If you saved your checkpoint to 1B and want to bring it back into your local storage, here's how. If you saved it as a 1B artifact, as we showed in the previous slide, then follow method 1. First, get the run object using your 1DB URL. You can find it on the 1DB website under your project and run ID. Once you have the run, use run.useArtifact to get the artifact. Then download it to your local storage. After that, you can load the checkpoint file with tar.load, just like loading any .pth file. Alternatively, if you saved your file using 1db.save instead of creating an artifact, then use method 2, which is a bit simpler. Just call 1db.restore with the run path, then use tar.load to load it. In both cases, the goal is to get the checkpoint file locally so we can load it back into the model later. Once the checkpoint is downloaded to the local, here's how to load it into your model. First, use tar.load with checkpoint file path to load the checkpoint file. Then use .load stateDict to load the weights. You can call it on the model with model.load stateDict. You can also call it on the optimizer or scheduler. One thing to note, when loading a checkpoint, make sure your model has the same architecture as the one you used to save the checkpoint. For the optimizer and scheduler, be sure to use the same type. For example, use the same atom, SGD, etc., so that the case can match. Otherwise, you'll likely get an error when loading states, because the case or layer shapes won't align. Now, let's talk about how to organize a model and load specific parts of it. In real practice, we often don't want to load or save the full model. For example, in homework 4P2, with transfer learning, we might only want to load the decoder and train the encoder from scratch. To do that, we need to clearly separate different parts of the model, and that's why organizing parameters properly is so important. There are two main ways to organize a model. One is to group your parameters into reusable submodules. The other is to organize them by layer names, like using sequential blocks. In this dummy network, we did both. Lower and upper layers are sequential blocks containing multiple layers. Each layer is automatically assigned an index like 0, 1, etc. Module 1 is our custom-defined submodule. If we print out all the parameters of the model, we can see that it's just a dictionary with a bunch of keys with names in them, and then they have a bunch of values. These names are very useful when you only want to load part of the model. You can filter the dictionary by key. For example, only keep keys that start with lower layer, and then use the method as before to load those weights. Here is a simple code demo on how to save and load checkpoints. We start with some setup. You paste your ONIB key here. Next, we define our model. This includes the dummy submodule and dummy network, which are shown before. Below that, we declare the model, optimizer, and scheduler. You can also print the model's parameters here to see what will be saved in the checkpoint. Here are a few ways to save your model. This is typically done inside the training loop, often at the end of each epoch. You can use tar.save to store key objects like the model, optimizer, and scheduler into a local checkpoint file. Be sure to set a runname here and update it in the blocks below. If you want to save the checkpoint to want to be as an artifact, run the save block below to upload it. Important, make sure to call wandb.init first, otherwise the sieving will fail. To load the checkpoint from wandb, run the next block to download the artifact into your local directory. Alternatively, you can use wandb.restore and then use torch.load to fetch and load the file directly. Once you have the checkpoint path, copy it here and load the checkpoint. From that dictionary, we can extract everything we saved, like the model state, optimizer, and scheduler state, and load them back. Let's say, for example, our runtime crashes. You can redeclare your model, optimizer, and the scheduler here. And then load their states using the saved checkpoint, and your training progress is recovered. If the crash happened mid-epoch, this is how you can pick everything and continue training. One thing to watch out for, if the model definition had changed, for example, if you change the layer's dimension, then loading the checkpoint will fail with a size mismatch error. See here? Then if we fix the dimensions mismatch to match the original one, then the load will work again. You can also load only specific layers if needed by filter the static. Here are some reminders we put together based on common issues students encounter during implementation. We encourage you to go through this before you start. It can help you avoid many frustrating errors. Hope this helps. Have fun on your journey and good luck.